You guys ready to become real algebra students? Time to bring out the real dish, the real meat and potatoes of algebra. We're going to start learning how to factor polynomials. This is probably going to be the most earth-shaking thing you've done. It's really not that bad because you've already been doing it, and I'm going to show you that you've already been doing it. So first off, really quickly, let's go over some vocabulary we might need for today. We'll grab the, let's grab the green pen. Yeah, factoring. Factoring, what does that mean? And GCF. GCF, this stands for greatest common factor. Greatest common factor. And in the past, we did the GCF with finding like the GCF of 24 and 16. The GCF of 24 and 16 is the largest number that we can divide both 24 and 16 by and get remainder 0. And that number is, of course, 8. 8 is the GCF of 24 and 16. But how do we see that? Okay, so we're going to be doing GCF today. That's the greatest common factor. 8 is the GCF of these two numbers here. And previously in the past, we used that for like simplifying fractions and stuff. But let me remind you, if you were to multiply three numbers, how do we do that? Well, we can multiply in any order. So let's do the first two, which would give us 14 times 9. And then 9 times 14 is, 9 times 10 is 90. 9 times 4 is 36, so 126. To understand this multiplication, we first need to, understand factoring, we need to first understand multiplication. When we multiply, obviously we're working our way down this way. Factoring is like you take something that is a finished multiplication problem and you are undoing your work and writing it as a product. This is the act of factoring. You take a number and then you write it as a product, usually as a product of primes if you're going to do its prime factorization. But the act of breaking it down into multiplication is the act of factoring. So let's go ahead and factor 60. Now, we could break it down any old way we wanted to, and you might be able to go straight to the prime factorization from here. Some people, maybe not. So that's okay. Basically, you just say 60 is what times what? There's lots of things you could choose here. 6 times 2, 5 times 12, 30 times 2, 6 times 10, I think is what I meant to say. So 6 times 10, break apart 6, that's 2 times 3, and 10 is 5 times 2. So you break the numbers apart as you work your way down. I can't break any of these, I can't factor any of these other numbers, so this is the prime factorization of 60. You guys, go ahead and give it a shot. Why don't you practice and factor 18? What is 18's prime factorization? Okay, here we go. 18 is 9 times 2, and 9 is 3 times 3. And we have our 2 that comes down along for the ride. So that is how you factor. You're just breaking it down into a product. You're really kind of doing division and leaving the multiplication problem left over. Here we go. All right, so last time we were multiplying by using the distributive property to multiply polynomials. We were multiplying a monomial times a binomial. If you do that, it's pretty straightforward. You're doing 6 times 5 is 30. X squared times x is x to the third. And then 6 times negative 9 is negative 54. X squared times y is x squared y. Okay, so today what we're going to do, today is different. Today we're not going to distribute x squared y. What we're going to do is we're going to start here. Today we'll start here, and we're going to end here. We're going to factor this expression. So this binomial, what we're going to do is we're going to look for a common factor between these two things, and that includes the numbers and the variables. So we're going to start here, we're going to end over here. We're basically undoing the distributive property. So I'm going to show you a quick way to do that. or a trick to do that, and then hopefully by the end of the video, you won't need that trick. So let's see our first example. The first example is 5x cubed plus 25x squared plus 45x. I want to write this as a product. Okay, well, to write it as a product, we first have to, I think it helps to look at the prime factorization of each term. The first term being 5 times x times x times x. The second term being plus 25 is 5 times 5 times x times x. The third term being plus 45. If you need to write it on the side, that's 9 times 5, which is 3 times 3 times 5. Okay, so this will be 3 times 3 times 5 times x. Great. So how do I factor a polynomial? It's really quite simple. You're going to go to each of the three terms, and you're going to see what are the factors in each term that they have in common. Now, I don't expect you to necessarily do this on every problem, because you might have 20 x's, and that would be absurd to do, right? So what we do is we go through and we are going to underline the things that they all share. Well, each term has a 5, so I can underline that. And each term has an x, so I can underline that. But if we go through and we say, does each term have a second x? Well, this one has a second x. Oh, but this one doesn't, so I can't underline that. This one has a second 5, but this doesn't, so I can't underline. And this one has a 3, but these don't have 3s. So there's no other factor in the terms that is shared amongst all of them. So what I do is I'm going to take 5x and I'm going to undo the distributive property. It's like I'm pulling it out and I'm going to put it on the outside of the parentheses. So that's going to be 5x times, what I have left is x squared plus 5x plus 3 times 3 is 9. You just multiply what is left. So the things that are not underlined end up in the parentheses. And the way that you can check your answer is you can redo the distributive property. You can say 5x to check your answer. You can multiply out 5x times x squared is 5x cubed. 5x times 5x, 5 times 5 is plus 25. 2x is x squared. 5x times 9x is plus 45x. Hey, look, that's what we started with. So you can check your answer by doing the distributive property, but we're trying to undo. And when you're done, you'll know you've pulled out the greatest common factor if none of the terms inside share a factor, which they don't. So this is our final answer. 5x times x squared plus 5x plus 9. And the 5x here is our GCF. Let's see. I'm going to do that in green so that it doesn't look like I'm pointing at the box. So that's our answer, but this is our GCF. This is the factored form of this polynomial. Now, we can factor this further, but today we're just focusing on the GCF. Okay, so we're going to factor this polynomial using the GCF. So I can write 5x plus 15 as 5 times x plus 3 times 5. Okay, what are the things that they share in common? Each term. This term has a 5, and this term has a 5. This term has an x, this one does not. This term has 3, this one does not. So our factored form, or when I pull out the GCF rather, what I'm going to get is 5x times x plus 3, whatever's left over. If you multiply that out, we'll see what we get there. Okay, in blue, let's do this one in blue. Oh wow, look at that. I have like a wear spot on my trackpad from changing the color. That's hilarious. Okay, anyways, just notice that. Okay, so let's break these down. 3x times x minus 12 is going to be 4 times 3, and 4 is 2 times 2, so 2 times 2 times 3 times x, and 15 is plus 3 times 5 times x. Now I'll go through with my purple pen. We're going to underline what they share in common. Each of them has a 3. Does each of them have an x? Yes, they do. Does each of them have a 2? Nope. Does each of them have a 5? Nope. Does each of them have 2 x's? Nope. This one's our limiting factor, so our GCF is 3x here. And what is left over, again, we're pulling that out, like undoing the distributive property. What's left over is x squared minus 4x plus 5. So multiply what's left in each term. Great. Okay, you try this one in green, and we'll go over it here in just a minute. You unpause the video. Jeez Louise. Okay, here we go. Go ahead and factor it down. 7yy plus 3 times 7 times x minus 7 times 2. The GCF is everything that's shared amongst each term. They each have a 7. And that's it. They don't share anything else. So our GCF is 7. And our factored form is 7 times, and then inside the parentheses, let me grab the green one, is y squared plus 3x minus 2. And you could multiply this out to check. 7 times y squared, yep. 7 times 3x, yep. 7 times minus 2, yep. Cool. All right, we're going to go over a couple other weird little scenarios that you can run into when factoring using the GCF. The typical rule is you pull out the negative when all the terms are negative. A -1 is part of your greatest common factor. So if we factor this, you get -2 times 3 times x minus 20 is 2 times 2 times 5. So go through, find those values. The only thing that they share in common is a 2, right? So if they both have a 2, and I just kind of underlined those 2's randomly, we're going to pull out a 2. The problem is, since both terms are negative, we're going to make them negative. Now remember, when I multiply this out, I need my answer. I need both terms to be negative. So what does that tell you about the sign of what's in here when I do the distributive property? Since these are both negative, I need both of the things on the inside to be positive. So what's left is 3x squared minus 10. 3x squared minus 10 on the inside. Now let's take a look at this one. Take a guess. What do you think the GCF is in this situation? It's negative x times x minus 2 times 3 times x minus 7. Well, great. That was a waste of time because they don't share anything. Well, that's not entirely true. They do share, they are all negative. Since every term is negative, what we're able to do is make our factored form -1 or just negative, and then everything on the inside will become positive, x squared plus 6x plus 7. It turns out there's sometimes in math when we pull out a -1 when they're not all negative, but for the sake of this assignment, when all the terms are negative, you factor out a -1. It's part of the GCF. Lastly here, we're going to have just a couple of, I want to go over how to factor this polynomial using the GCF without doing this method, because look at all the things we're going to have to write. It becomes fairly tedious. So I'm going to give you a kind of a walkthrough of how you do it without writing everything out. And you might need to listen to this a couple times for it to sink in. Maybe you can practice it on the other problems. But you find the greatest common factor of 28 and 24. To do that, it's the largest number you can divide 28 and 24 by and get remainder 0. The largest number you can do that with is 4. So in the way, my strategy there is like look at the smallest number and then kind of try that. If that doesn't work, find, factors of that. Okay, so we're going to pull out a 4. Now let's think about the variables. How many x's do they all share? This one has 2, this one has 3, this one has 2, so they all have at least 2. This one has 5, this one has 3, this one has 1. They all have at least 1. Basically, you take the smallest power of the terms that are present. And now we have to go through and write what is remaining. And this is what's a little bit hard. We are undoing the distributive property. The distributive property is multiplication, so we're really dividing. 20 divided by 4 is 5. I pulled out 2 x's. This has 2 x's, so they go away. I pulled out 1 y, so there are 4 y's remaining. Minus 8 divided by 4 is minus 2. There are 3 x's here. I pulled out 2, so there's 1 left. There are 3 y's here. I pulled out 1, so there are 2 left. Lastly, 24 divided by 4 is plus 6. There are 2 x's here. I pulled out 2, so there are none left. There's 1 y here. I pulled out 1, so there are none left. So that's our final answer. This is this polynomial in, or after factoring out the greatest common factor. Okay, what about this one in red? In red. There's an issue here. Doesn't matter what we do, this is not, they have no common factors. 15 is 3 times 5, 7 times x. There's nothing that they share. So when you have one that's like this, typically we call this, we say that it can't be factored. Its greatest common factor is equal to 1. 1 is the largest number I can divide both terms by. You also might say, just like with a regular number, when it says like 23, we can't break that apart because it's a prime number. So sometimes we call these prime polynomials. Okay, last one here. Let's take a look. If you're using that kind of break apart method that we looked at before, that was 2 times 3 times x minus 3 times x, and we go through and we find the GCF. What do they share in common? They both have a 3. They both have an x. Oh no, I've pulled out the whole term. What do I do when the whole term gets pulled out? Well, we're pulling out 3x, so it's going to be 3x times what's left over? 2x in the first term, that's easy, but nothing is left over here. The problem is it can't be 0. Because if it's 0, when I multiply back out, I don't get 3x. I need whatever this to be. When I multiply it by 3x, I get negative 3x, so this has to be negative 1 in order for that to be true. Negative 1, because I could just tack on a 1 right there, and it would still be the same problem, right? Cool. All right. That's it. Hope that made sense. Let me know if you need to see some more problems, and good luck on your first steps factoring using the GCF.